Okay, so this is the second half of question 5, D, E, and F. So now we have a situation where my 2, where's my 2? My 2 and my 2 had now been replaced with K and K. And when I graphed over here, when it was 2, it had a turning point at 2 and 1. I wonder if I change that to 3 and 3 and 3, whether it would then have a turning point at 3. And it does. Okay, so I want the turning point of H to always lie on this line here. So the y coordinate of the turning point has to be on 2x to the power of n. Okay, so I believe that the y coordinate of the x coordinate of this will be k, but I'll just double check. So I'm now going to come back up here and I'm going to put a k there. And I'm going to put a k there, or I'm going to divide by k. And that gives me this expression. So I'll copy that and I'll paste it. Now, if I was to take the derivative of that and set that equal to 0 and solve, for k, and get rid of that at the front, I get x equals k. So that's correct. So the turning point will be at k. If I sub k back into here to find out the y-intercept, so I take this and math 3 given, let's make x equal k. Then I have the coordinates of the turning point are k and 2 on x. So if I'm saying that the y values of the turning point and the y value of this are equal, I've got 2 on x has to equal 2x to the n, therefore n has to be -1. Okay, 1. And we're looking for the kissing point. We're looking for when A and H intersect once. And since we have this curve that isn't quadratic, it's got an exponential involved, and the inverse has a logarithm involved, I'm going to do the kissing bit, which either is I take h of x and make it equal to x, and I'll take the derivative of h of x and set it equal to 1 and solve for x or k, or I can use the inverse. Since they've gone to the bother of giving me the inverse, I think that might be a hint that I should use the inverse. So I've got the inverse typed here. I've got the inverse typed here. I've got the derivative. And then I come down and I have the derivative equal to 1, and I have the inverse equal to x, and I'm solving for x and k, and it gives me more than one solution, and I get x equaling 1.866 and k equaling 1.27. So I'm going to say that the smallest value of k is 1.27. And in the last part of the question, it is possible for the graphs of h and the inverse of h1 to intersect twice. This occurs when k equals 5. Okay then, so if I take my expression, which is this expression, into a new line, that's the inverse. Hang on, I'll just... So I want the original when k is 5. So I'll copy that to see what's going on. Post, given k equals 5, I believe that it will have a turning point over at 5. Variables k equals 5. Open up the graphing window. Get rid of everything that's already there. Pick this up, drag and drop. And if I was to analysis sketch the inverse, now I know previously that the G1 inverse was the top curve. So if I'm doing the H1 inverse, it's the top curve. So I'm looking for the area in here. Okay, so what I might do is find those intersection points. Let's take this, let that be Y, let that be Y, all that equal to X, and solve for Y. And I want the positive square root, not the negative square root, because I want the inverse of H1, which is the top one. So if I take this and drag and drop that, beautiful. Okay, let's think about analysis memory initial. Okay. And if I grab this and drag and drop this, that's the intersection point that I'm looking for. So let's find those intersection points. 1.45. So area is going to be the integral of 1.4509124 through to 8.78 15745. My top curve is the H1 inverse of x minus h of x dx. But I'm going to use my calculator because it says 2 decimal places. Analysis G solve integral of the intersection. I'll accept that one. I'll go across to that one. There's my answer, which is 43.9139. And we're doing 2 decimal places. 43.91 square units is going to be my answer.